Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. The starting material is acinephthalene, which consists of a naphthalene unit fused with a 5-membered ring that contains 1C is equal to C double bond, the 1,2 double bond of the 5-membered ring. Its molecular formula is C12H8. Moving on to the next step. Addition of 1 equivalent of HBr to acinephthalene gives C13H17Br. Weight acinephthalene is C12H8 and HBr adds across the double bond to give C12H9Br. C12H8 plus HBr is equal to C12H9Br, which is C12H9Br, not C13H17Br. Re-examining, the product is C13H17Br. The starting material shown has molecular formula consistent with acinephthene or a partially saturated analog. Looking more carefully, the starting material appears to be a tricyclic structure. It looks like acinephthalene, C12H8, but the product C13H17Br suggests a larger starting material. Actually, counting the structure, it appears to be a fluorine-like or phenylene-like structure. The structure shown is acinephthalene fused with an additional ring. This is actually a structure with formula C13H16, acinephthene with an extra CH2, or fluorenthene partially reduced. Given C13H16 plus HBr is equal to C13H17Br, the starting material is C13H16, which is consistent with the tricyclic structure shown, acinephthalene with one additional CH2 giving a larger 5-membered ring, i.e., fluorine type or acinephthene extended. Moving on to the next step. HBr adds to the C is equal to C double bond in the 5-membered ring following Markovnikov's rule. The proton, H+, adds to the carbon that gives the more stable carbocation. In this fused ring system, the carbocation formed at the benzylic position adjacent to the aromatic naphthalene system is more stable because it is stabilized by resonance with the aromatic pi system. And for the final step, the proton adds to the less substituted or less stable carbocation forming carbon, and Br then attacks the more stable, more substituted benzylic carbocation. Both carbons of the double bond in the 5-membered ring are benzylic, but the geometry and substitution dictate which carbocation is more stable. Since no rearrangement occurs, Br ends up at the more stable carbocation position. The bromide ion attacks the carbocation from the less hindered phase. In the fused ring system, the less hindered phase leads to the product shown in option D, where Br is on a plane, equatorial anti-bond at the terminal carbon of the 5-membered ring. A shows Br on a wedge bond. This would be the more hindered phase attack, not the major product. B shows Br at a different regiochemical position inconsistent with Markovnikov addition. C shows Br on a dash bond. This corresponds to SYN addition from the more hindered phase, not the major product. D shows Br in the correct regiochemical position with correct stereochemistry, attack from less hindered phase, consistent with Markovnikov's rule and no carbocation rearrangement. Therefore, the correct answer is D. Therefore, the correct answer is option D.